Picture yourself designing a smart greenhouse. Your plants need constant monitoring, but the sensors you connect don't speak in ones and zeros, they speak in shades of voltage. Cover an LDR with your hand, and a voltage drops. Shine a light, and it rises. That's messy, continuous, analog data. The ESP32 ADC, or analog to digital converter, is the bridge that transforms that smooth voltage into precise digital values we can actually process in code. In this lesson, I show you how to configure the ADC, read real sensor outputs, and map those raw values into meaningful units like brightness or temperature. By the end, you'll not only understand what the numbers mean, but also how to use them to drive real-world automation. Think of the ADC like a ruler with 4096 tiny marks along its length. On the ESP32 that ruler covers the range from 0 volts to 3.3 volts. So every digital reading corresponds to a very small slice of voltage, about 0.8 millivolts per step. For example, 0 volts is step 0, 3.3 volts is step 4095, and 1.65 volts lands near step 2048. What matters is not just the math, but how it maps back to your sensor. If you're measuring temperature, you'll use a calibration curve. If you're monitoring light with an LDR, you'll interpret higher or lower voltages based on brightness. Always remember, the ADC doesn't give meaning, it gives numbers. You add the meaning through calibration and context. Here's a quick table that illustrates how ADC values translate into voltages on the ESP32 Notice how a mid-scale reading directly corresponds to half the supply voltage. This mapping is crucial because whenever you print an ADC value, you should also convert it into volts for interpretation. Once in volts, applying a sensor-specific formula, like temperature scaling or light resistance curves, becomes straightforward. Let's wire an LDR using a voltage divider. The idea is simple. Connect one leg of the LDR to 3.3 volts, connect the other leg both to the ADC pin and to one side of a 10K resistor, then ground the other side of that resistor. This way, as the LDR's resistance changes with light, the voltage at the ADC input shifts proportionally. Bright light lowers resistance, raising the voltage. Darkness increases resistance, lowering the voltage. The ESP32 reads those changes as varying ADC values. This divider design is universal. You'll use it again for soil moisture probes, photoresistors, or even battery monitoring. In code, we'll keep it simple. We read the ADC pin using analog read, normalize the raw value into volts, and then map that range into a percentage for readability. Think of the percentage as a crude, light level, meter. In real projects, you'd refine this further using calibration data or by logging values under known conditions. For testing, use serial monitor. Shine a flashlight and see the number rise, cover the LDR and watch it fall. This immediate feedback loop is your best debugging tool. When readings feel noisy, average multiple samples before printing. The point is to treat the raw data as your starting material, and then shape it into something useful for control decisions. Engineers often trip over a few recurring issues when working with ADCs. First, never leave an ADC pin floating. Without a proper circuit, it will show random numbers. Second, remember that your ESP32 cannot tolerate voltages above 3.3 volts, so always scale higher inputs with resistors. Third, sensors like LDRs are nonlinear. Don't assume percentages are absolute. If accuracy matters, calibrate with real-world references. Also, noisy USB supplies can spoil readings. Adding a capacitor across your voltage divider often smooths this out. Debug systematically. Start with raw ADC values, then layer on voltage conversion, and finally map to units. That hierarchy keeps problems easy to isolate. Once you've got ADC basics working, expand into small projects. Replace the LDR with a TMP36 temperature sensor and calculate degrees Celsius. Wire a resistor divider to measure battery voltage safely. Add an LED that automatically turns on when your LDR shows darkness. Or, for more fun, log ADC readings to the Arduino serial plotter and visualize how sunlight changes through the day. Each of these extensions trains a different muscle: calibration, scaling, control logic, or visualization. The trick is to take the same ADC reading concept and repurpose it into varied, practical use cases. In this lesson, you learned how the ESP32 ADC transforms analog voltages into usable digital data. You saw how to wire a simple voltage divider, read raw ADC values, convert them into volts, and then map them into meaningful units like light levels. Along the way, we covered pitfalls, calibration strategies, and practical design tips drawn from real-world automation projects. With this knowledge, you can now treat the ADC as a universal translator between the messy, analog real world and the clean, digital domain your ESP32 thrives in.